All right, now question 6 through 8. These are going to actually refer to pretty much the same free body diagram, but there's going to be a couple changes as the problem evolves. So first, the free body diagram in general, we're going to have a normal force, we're going to have a weight, we're going to have the applied force, and we're going to have a kinetic friction force going backwards. Now for the first part of this three-parter, problem 6 through 8, it's being pushed at a constant velocity. And so what that means when we set up our equations is that the applied force balances the kinetic friction and the normal balances the weight. So if we want to get the coefficient of friction, we actually have to go ahead and plug in some of our numbers. So I know that the friction force from the problem is simply 10 newtons. I also know that since the normal is the weight, that's going to be 2.5 times 9.8. And I'm not even going to bother to solve for that because what I'm going to use is the third equation, which is friction is mu times the normal force. So I have 10 equals mu kinetic times my normal force, which is 2.5 times 9.8. And that's how I'm getting 0.41. Now, in the problem that follows, number 7, we want to know the acceleration of the blocks. And somebody pointed out something really important to me. The way this problem should have read is, let's change it. Let's put the word now in front, as if to say, now we're going to change things. We're going to now have the net force be 1 newton. In this problem, let's be clear, the net force is 0, which is why it's sliding at a constant velocity. So now we have an unbalanced force. So what that means is we have the applied force, the kinetic friction going backwards, and the effect is that the mass accelerates. Now to get the net force, that's going to be this left-hand side here. So I suppose I could move this down and just kind of remind myself that this is the net force equals ma, and I expand that out as Fa minus Fk. So we have 1 equals 2.5, the mass that I'm getting from here, times A. And so A is going to be 0.4. Now that's the only choice that we have here, 0.4 meters per second squared. So we know that that's the only choice, but we can kind of check to get the applied force. The applied force, that's Fa minus the kinetic friction, which we got previously is 10, equals 2.5 times the 0.4, which is 1, which is what we expect. So the applied force is going to be 11 newtons. So we're definitely right on that part. Finally, we ask the question, if the box is traveling at 5 meters per second, and then we suddenly wipe out the friction, what's going to happen? Or we wipe out the applied force, what's going to happen? So let's just take this free body diagram from here and move it down to this problem and make a little change. And here's the little change we want to make. We are now going to wipe out the applied force. So we had an applied force, and that suddenly vanishes to 0. So I still have unbalanced forces since I'm going to accelerate, but this time coming to rest is a form of acceleration, I'll have 0 minus the kinetic friction, 0, because the applied force is now 0, equals m times a. So I'm going to have negative 10 equals 2.5 times a. We're going to get a new acceleration, which is negative 4 meters per second squared. And now I can get the time it takes to rest as v equals at plus v naught, or 0 equals negative 4 times t plus 5, the initial speed, and 0 is the final speed because that comes to rest. And so I'm going to get 1.25 seconds as my answer for number 8.